What is center of gravity and how is it different than center of mass? So, those are the questions I want to address in this topic because we're going to be referring to center of gravity. And it's easy to get confused or wonder, like, which one is the correct one to use right now? And sometimes either one, depending on the situation. So, I've put here the definition from Wikipedia for center of gravity. It says a body's center of gravity is a point around which the resultant torque due to gravity forces vanishes. Now, what is it talking about there is that if you take a real object, that object has many constituent masses in it, right? I mean, if you think about all the molecules in that object, all the atoms in those molecules, and then within those atoms, there are protons and neutrons and electrons that are actually super tiny. Maybe we don't need to worry about those, but they're still there. They contribute a small fraction of the mass. Um, the protons and neutrons are actually made out of quarks. I don't know how far down we have to go here, but you kind of see what I'm getting at. Is each of those objects has weight, and so each of those constituents has a gravity force in principle. And so that's kind of what the Wikipedia definition is referencing to. It's kind of makes my head explode to think about all that. So I have a more practical definition that I think is kind of the same as this, is that the center of gravity is where we can regard the force of gravity to act as a single force equivalent to all those forces that we're talking about here in reality. Now, I don't necessarily mention explicitly in my statement here, the one that's labeled Kramer, right, for me, the notion of torque, but it turns out if you can define where a force acts on a system, that means you can define the torque associated with that force. And the Wikipedia definition is saying the center of gravity point is the point at which the torque due to gravity would vanish or be equal to zero. Well, since I'm saying the center of gravity is where you can pretend that the force of gravity acts as a single force, if that is going to be the point of reference, if you're like thinking about rotations around that point, in other words, when we say like we're going to define torque, right, we always need to have some defined rotation axis, or at the very least a point of reference that allows us to define moment arm vectors, right? Well, as a single force equivalent, if we define moment arms relative to this point, the force of gravity is going to apply zero torque around the center of gravity point if that's where we think of gravity as acting. So in some ways, with my definition, I've captured in a maybe simpler and more practical way what is a really deep mathematical and possibly brain cell exploding idea. Now, the other question I raised at the beginning, though, is like, well, how does this relate to center of mass? They are different, right? Because we've seen here that the center of gravity is kind of based on this notion of where we can think of the force of gravity acting. And it's kind of also the balance point, right? Well, I argued earlier, really starting, I think, in the last chapter, that the center of mass is also the balance point of a system. And it turns out, maybe I lied a little bit. That's true here on Earth, but it may not be true everywhere. It turns out to be true if the effect of gravity is uniform throughout the space that you're interested in, which basically means it's the same strength and points in the same direction through that space, which tends to be true near the surface of the Earth. Maybe it's not 100% true because, you know, the Earth curves, right? So, in fact, if you look out to the horizon, that's usually, they say, about 20 miles away, right? Roughly where the curvature of the Earth becomes noticeable. And in that sense, if you said, like, well, is gravity going to be perfectly uniform over a distance of possibly hundreds of miles, much larger than 20? In other words, the answer might be no. But on the other hand, usually we're not considering extended objects of that size when we're applying these concepts. We haven't gotten to that point in our technology to be constructing things that big just yet, although there's some cool movies with those kind of ideas, right? Anyway, so in that sense, I've written here the center of mass definition to be clear. Really, center of mass is defined just based on a distribution of the masses. And we've seen examples where we had two masses and we had to calculate their center of mass point. I've written this here as to like, hey, there could be any number of them. There could be thousands of them, right? But you're simply going to add up mass times position for all of those and then divide by total mass to kind of get that average position for the masses in an object. But like I said, we'll look at this. I'm going to actually show you a proof in the first example. It's maybe a little bit advanced, but just so you can really believe what I'm saying here, that in uniform gravity, these two are equivalent. But again, they are kind of saying different things because center of mass is more about mass specifically and center of gravity is more about where gravity acts.